Students, it's Nazia Begum here, your physics lecturer, welcoming you all in today's class. So in previous class we have studied about classification of solids in terms of resistivity and conductivity. We have also studied about different energy levels inside atom in which electron can exist. Okay, then we have also studied about splitting of energy levels in form of energy bands, and we have seen that in their course of separation splitting, two bands are generally formed in crystals. Okay, in crystal atoms are close to each other, and that's why two energy bands generate there. One is valence band, other is conduction band. Between valence and conduction band there is forbidden gap. In forbidden gap, as the name suggests, no electron can exist. Okay, electrons are forbidden at that gap. They cannot remain there. They can either be in valence band or in conduction band. So if the electrons are given sufficient amount of energy, so they can jump from valence to conduction band. And as the name suggests, conduction band is that band from where the electron can move or can conduct electricity. Okay, now let's discuss the definitions of valence and conduction band and forbidden gap. So here is important energy bands in solids. First, valence band. The energy band occupied by the valence electrons is called the valence band. Depending on the number of electrons, this band may be completely filled or partially filled, but it is never empty. For example, in case of inert gases means that gases which do not react with uh, any other material. In that type of gases, valence band is full, but for other materials it is only partially occupied. Second is conduction band. The energy band which accommodates only those electrons which come out of a valence band is called the conduction band. The electrons are responsible for the conduction of current in a conductor, hence they are called the conduction electrons. All electrons in a conduction bands are free electrons. Okay, if the conduction band is empty, there will be no conduction of current in that material. Okay, so if conduction band is empty, so the material is insulator. For example, all insulator have empty conduction band, but conductors have partially filled conduction band. Then is third is forbidden band. The energy gap between the top of the valence band and the bottom of the conduction band is called the forbidden band or the band gap. This region has no permitted energy levels, hence no electron can stay in this region. The larger is the width of the forbidden band, more tightly are the valence electrons bound to the nucleus. If an electron in the valence band receives energy from external source equal to the forbidden energy gap, it moves up from the valence band to the conduction band and becomes a conduction electron. So as I have already told you, okay, what is forbidden gap? Forbidden gap is the distance between uppermost part of valence band to the lowermost part of the conduction band. Okay, between these two parts, whatever area is there, that is called forbidden gap. It is having a certain amount of energy. If electron in valence band get the energy equal to Eg, forbidden gap 1, so they can move to conduction band. And when electrons go to conduction band, then only they can conduct electricity, otherwise not. If conduction band is empty, no current will flow through any conductor. Now let's classify conductors, insulators, semiconductor, means classify the solids in terms of conductor, insulator and semiconductor in terms of the energy bands. Okay, so in conductor what happened? there are partially filled valence band. When the valence band is partially filled and an electric field is applied, the uppermost electrons acquired kinetic energy and move to any of the large number of available empty higher energy levels within the band. As a result, they move an electric field is applied. When an electric field is applied, sodium and other alkali metals belong to this category. Similarly, the noble metals Cu, Ag and Au also have half filled bands. Copper, gold and silver, they have half filled bands. Okay, so here you can see partially filled valence band is there. Okay, when electrons are given sufficient energy, they can easily jump to conduction band. In conductor, one more type of band arrangement you can see, where you can see here that valence band, this is valence band, sorry, boundary, this is valence band here, the shaded blue part you can see, okay, and this is conduction band. So you can see this region of conduction band and valence band is overlapping each other. Okay, that means whatever electrons are present in valence band, they are actually present in conduction band as well. That means here the conduction of electricity is very easy. Okay, so if this type of band exists, that material is a very good conductor. Then we have insulators. In insulator, the valence band is completely filled and the conduction band is empty. A large energy gap, okay, whose energy is more than 3 electron volt, separates divalence and the conduction band. Hence, the electrons from the valence band cannot move to the conduction band and insulator therefore is unable to conduct current. Now the next one is semiconductor. In semiconductor, the valence band is completely filled and the conduction band is empty, and a small energy gap separates the two. Okay. In case of gallium and silicon, the forbidden gap is 0.72 electron volt and 1.1 electron volt respectively, which is very less. So that's why what happen, if electrons are excited a little, they easily jump to conduction band and the material become conducting. Okay, so initially the valence band is fully filled, but when energy is given, it becomes the electron moves to conduction band and the material becomes very conductive. The highest energy level occupied by an electron in the valence band at 0 Kelvin is called Fermi level, and the corresponding energy level is called Fermi energy. Semiconductors at 0 Kelvin behave as perfect insulators, but at room temperature, some electrons from the valence band acquires sufficient thermal energy and move to the conduction band. This causes electric current to flow in them under the influence of the applied electric field. The resistivity of such material lies between the insulator and conductor. Hence, they are named as semiconductors. Now, the next topic is current carriers, that is electrons and holes in semiconductor. So here you can see in figure A and B. Okay, two bands are there, valence band and conduction band. So here you can see that valence band is completely filled and conduction band is completely empty. Okay, when the energy is supplied to these electrons, so whatever electrons which lies on the upper part of valence band, they get the energy and they move to conduction band. When electron move to conduction band, okay, when they leave the place, their empty place is there, which we call as hole. We can say that when electron leave their place, a hole is generated there. So when the electron left the valence band and go to conduction band here, okay, so 5 electron goes to conduction band, so we can see that 5 holes are generated here. Okay, and these electrons and holes are the charge carriers in a semiconductor. See, holes are actually not the charge carrier, they are not movable. Actual motion happen in electron only. Okay, holes are non-movable, but they can also considered as a charge carrier. Why? Now suppose if more energy is given to the electrons present in valence band, so these electrons first jump to next hole. Okay, the electron, this one, will first next jump to this hole, and here the electron will be filled. Okay, in this hole the electron will be filled and this hole will become empty. Let me show you with this. Suppose this is valence band. Here we are having one electron, here another electron, and here we are having hole. When we give energy to this electron will directly not go to the conduction band. Okay, but it will slowly move its increase its level, and then it will go to conduction band. Okay, so what happened? First this electron, when it will get the energy, it will jump to this hole. Then this place, here electron will occupy the place, and here from where the electron has moved, this place, here one hole will be created. So that means as the electron is going up, we can see that hole is moving down. Okay, so actual motion is there in electrons. Because of electrons, holes are generated. Whatever place the electron left, their holes are generated, and we feel that holes are also moving in backward direction. Okay, but holes are not moving. So these electrons and holes, they are called current carriers in semiconductors. Okay, here is one definition of hole. See, an electron moves from the valence band to conduction band. A vacancy is created in the valence band at the place where the electron was present. That vacancy is called hole. So here you can see in blue line it is written, this vacancy with the effective positive electronic charge is called a hole. So in electron negative charge is there. Okay, so in hole we assume that positive charge should be there, because generally all the materials are neutral. So if electron is negative, so that hole should be positive. Then only the negative and positive neutralize each other. So we consider that hole is having positive charge. Okay, and in pure semiconductor, the number of electron is equals to number of hole, that we have seen in previous figure also. 5 electron jumped to conduction band and 5 holes were created there. So in pure semiconductor, Ne, number of electron, is equals to number of hole, Nh. Okay, now here you can see the crystal structure of pure semiconductor and current carrier. So here in silicon you can see, okay, 4 electrons are there. Okay, and if any electron move, a hole is created there. So here you can see in silicon, this is one hole, and this arrow sign is indicating that one electron has left the hole and become free. So whenever one electron become free, one hole also will be generated there. Here you can see that. If suppose more energy is supplied, here also you can see one electron left its plates and become free. So one hole is created. If more energy we will supply, so another electron will also leave the place, and whenever electron leave its place and become free, one hole will be generated there. So the number of free electron and hole, okay, not number of electron and hole, but the number of free electron and hole is equal in a pure semiconductor. Okay, now let's discuss types of semiconductor. We basically have two types of semiconductor, intrinsic and extrinsic. Intrinsic semiconductor means pure semiconductor which are found in nature Okay, and we don't have to do anything to make them semiconductor. So a semiconductor in pure form having no impurity atoms is called an intrinsic semiconductor. In pure semiconductor or intrinsic semiconductor, the number of electron, free electron and hole is equal, and they are having a valency of 4 electron. Keep that in mind. Okay, and gallium and silicon, you can see the electronic configuration here. At room temperature, some electron breaks away from the bonds and become free. At the same time, equal number of holes are created in the bonds. Hence, conduction in an intrinsic semiconductor is due to the motion of the electrons in the conduction band and holes in the valence band. Holes are created in valence band only. This thing also you keep in your mind, that whatever current is flowing in a conductor, so because of current the motion of because of electron the motion is there. Okay, and electrons are moving in conductors and holes are conduction band. Electrons are moving in conduction band and holes are moving in valence band. The electrons and holes responsible for electrical conduction in an intrinsic semiconductor are called the intrinsic current carriers. Okay, so here you can see this diagram. Here electrons are moving from negative to positive terminal. These are electrons, they are moving from negative to positive terminal, and these are holes, they move opposite to electrons, so they are moving to from positive to negative terminal. Okay, one more thing which we should discuss here is that mu equals to V upon E, where V equals to E upon m into tau n is the drift velocity of the charge carriers. As the movement of the holes in the valence band is due to the movement of the electrons. If electron will not move, there will be no motion in holes. Okay, holes actually don't move, but they appear to move because of motion of electrons. So the motion of holes is because of motion of electron. In the valence band, the electrons in the conduction band drift more freely than the holes in the valence band. Are you understanding this? In valence band, if the electron will move, then only the holes will move. And in conduction band, free electrons are there, so they are moving in a more free manner. In conduction band, movement of electron is more than in valence band, and that's why in valence band the movement of hole is also very less. So obviously the mobility of electron is greater than the mobility of holes. Okay, mobility is given by V upon E. Mobility is mu, which is given by V upon E. V is velocity, and if E is constant, okay, electric field is constant, so we can see mobility of charge carriers is directly proportional to velocity. So because velocity of electron is more in comparison with holes, that's why mobility of electron mu E is greater than the mobility of holes mu H. Now the next topic is in extrinsic semiconductor. The process of deliberate addition of desirable impurities in an intrinsic semiconductor is called doping. See, intrinsic or pure semiconductors are having equal number of free electron and holes. Okay, and they conduct electricity in a proper manner. But if we want to make it more conductive, if we want more electricity from the semiconductor, so we mix some impurities in it. Okay, sometimes we mix the impurities to increase the number of free electron, sometimes we mix the impurities to increase the number of holes. Okay, so whenever we are mixing any impurity in semiconductor to make it more conducting, okay, more powerful, so that type of semiconductor is called extrinsic or impure semiconductor. Okay, and the process by which we are mixing the impurity, we are adding the impurity is called doping, and the impurity atoms are called dopant. The impurity atoms, here is written, the impurity atoms so added are called dopants, and the semiconductor with impurity atoms, that is the doped semiconductor, is called the extrinsic semiconductor. Okay, and here is written some qualities of dopant, that the dopant should be such that it substitutes only a few, very few intrinsic atoms in the crystal lattice. Its size is almost the same as that of semiconductor atom. It does not distorts the original intrinsic lattice. And doping can be achieved by these three means: adding the dopant atom in the molten form of the intrinsic semiconductor. Okay, if the intrinsic semiconductor is in molten form or in liquid state, that time only we mix the dopants. Second, heating the intrinsic semiconductor in an atmosphere containing the dopant atom, then also they will react and combine with each other. Third, bombarding the intrinsic semiconductor with the ions of the dopant atom. It is important to note that doping is effective only when the sample of semiconductor is extremely pure and dopant atoms are such that they do not distort the crystal lattice. They do not disturb the crystal structure of pure semiconductor. Okay. So today we have discussed about intrinsic and extrinsic semiconductor. In next lecture I will tell you how to make different types of extrinsic semiconductors. Okay, so this is it for today's lecture. See you in next lecture. Till then, goodbye, take care, do some productive work, and the most important thing, be happy.